So it's an improper integral if we have infinity as part of the limits of integration. So we could do this like we would do it if it was just a plain old constant up there. We could try to find the antiderivative. So it's got 1 over x. That makes me think the antiderivative will be something along the lines of natural log of x, because the derivative of this term is 1 over x, right? But this term's a little bit different. They've got a 2 in the denominator. If you had a 2 in the denominator, you took a derivative, because of the chain rule, it'd be 2 over natural log. Sorry, 2 over. Well, let me think about that. That'd be 1 over 2x times 2 over here. Okay. So when we try to find this antiderivative, we got to put a plus 5 in there. The derivative would be 1 over 2x plus 5, which is what we have up here, right? So this looks like it's going to be the antiderivative, except for one thing. We need to multiply this by 2 because of the chain rule. So in order for this to be the proper antiderivative, we need that 2 to be gone, so we're left with exactly the same expression. So to make that happen, we want to have a 1/2 on the outside. So long and short of it is, the antiderivative of this term is 1/2 natural log 2x plus 5. And then we're evaluating the limits of integration from 0 to infinity. Now, no problem plugging in 0, because natural log 5 is a number. But infinity, if we try to think about the limit of this function as it goes to infinity, a logarithm does slow down in its rise, but it never stops increasing, right? The function keeps leveling off, but a logarithm never stops increasing. So if you try to substitute infinity, you're going to get infinity. It's going to be infinity subtracted by 1/2 natural log of 5. So we call this a divergent integral. So the correct choice here is that it diverges. Because, and again, that's because if you plug in infinity, we get infinity. So this integral, on the other hand, let's just go through the steps, valuing the antiderivative. So the derivative would be itself times the derivative of the exponent here, times -4. So to compensate for that, I'll factor out a 1/4. And now you can check it. If you take a derivative, it's itself times -4. So that makes the negative sign and the 4 cancel out. So this is the antiderivative. If we evaluate the limits of integration, infinity this time makes this pinch down to pinch to 0, right? Because if you do -1,000 in your calculator, and then if you do -10,000 in your calculator, what you're evaluating is 1 over e to the 10 to the 1,000, or 1 over e to the 10,000. So this is a huge number. 1 divided by a huge number gets really close to 0, right? So as x approaches infinity, this term goes to 0. So that's the first one. And then if you plug in -1, there's no problem there. You get e to the -4 times -1 makes e to the 4th. So this is -3/4 e to the 4th. So just 3/4 e to the 4th, because the negatives cancel out. So that one actually is not divergent.